on a single page. So, as another example, when I introduced this first last week, I spoke about magnets and things like gravity and such. But another nice example to illustrate exactly what forces are about is just if we consider the following. Let's say we've got a single electron. Now all of you hopefully know what electrons are kind of. They're little negatively charged particles and they've got to do with electricity. But an electron basically has got two important properties for us. The one, it has got a mass, but it's an extremely tiny mass. So it's something like 9.1 times 10 to the minus 31 kilograms. So electrons are very tiny things, and they carry electrical charge. Now, because an electron has got mass, it is susceptible to gravity, so it will feel a gravitational pull. So let's say I've got a single electron above the Earth. We know this electron will be pulled down by gravity. And we know that when we did projectile motion, any object close to the surface of the Earth, if we neglect the effects of friction or air resistance, has got a certain acceleration. So, like any other object with mass, due to gravity, this electron will accelerate downwards at a rate of 9.8 meters per second squared. And we know that is because of gravity pulling this electron down towards the Earth. Now, you might already also know that if I've got two electrons close together, things with the same charge push each other away. You might have done examples of this in high school. If not, we will do this later on in the year. So if you don't know this, you can just take my word for it. Electrons, because of their charge, if I've got a negative charge and a negative charge, they don't like to be together. They push each other away. And we can actually calculate the acceleration produced by that. So if I've got an electron over there, and I've got another electron over here, let's just to keep things the same, let's say that was 1 meter. If I put two electrons close by, both of them 1 meter apart, they push one another away. So this electron is pushed in that direction, so it accelerates away upwards. And we can calculate that acceleration. That's once we've done electrostatic forces and all of that, you'll be able to put some numbers to that. But just to give you an idea, the acceleration for this setup that this electron experiences is 252.7 meters per second squared. So if you look at this, we've got gravity and it produces a certain acceleration. We've got a different force, which is the electrostatic force, and it produces an acceleration that's almost 25 times larger. So if we decide both of these things are forces, which one would you say is the strongest? So if gravity can produce an acceleration of 9.8 meters per second, if I replace the entire Earth by a single electron, I get that suddenly the acceleration is 25 times larger. Which one is the largest force? Who says second one? Who says, I don't know? Who's not listening? Well, the second one is much larger because it produces a much bigger change in the motion of an electron. And this is essentially what a force is. These two things are fundamentally very different. Gravity and electrostatic forces, from where we sit, have got nothing to do with one another. The fact that an electron is attracted to the Earth because of its mass and it's repelled from another electron because of its charge doesn't have anything to do with one another. But we can explain these two vastly different phenomena by a single concept, and that concept is force. And the kind of unofficial definition of a force that I'm going to be using throughout is a force is if any object changes its motion due to an interaction with another object, or because of the removal of that interaction, so if either of this holds, so if the object changes its motion, either because it's interacting with an object or because I've taken an object away and now it's changing its motion, then we can say there's a force on the object that changes its motion. Right, so that is the kind of unofficial definition of a force that I will be using. Anytime I've got one thing, here's another thing, this thing changes its motion because it suddenly is aware of this thing, there must be some sort of force acting on this object. And the example that I discussed a bit, but would I just want to go into a bit more detail yesterday, is just this idea of, let's say we've got a box, and this box is on a table, and this table is on the earth, and again the earth is not to scale. So if we just look at this, right now the box is doing nothing. If the table were to suddenly disappear, so if suddenly the table now disappears and we only have the box suspended above the earth, we know suddenly that the box will fall, it will move downwards, so it will accelerate downwards with g is equals to 9.8 meters per second squared. So we've removed an object from the system and suddenly we find the box changes its motion. So when we remove the table, box changes its motion. How does it do it? It accelerates. Therefore, there must be some force from the table on the box if we were to put the table back. Because the moment we take away the table, suddenly motion changes. If we now take away the earth, so the earth suddenly disappears, which should leave you all quite feeling uncomfortable. We've just got the box over here and it just drifts in space. So it's not accelerating. So if it was accelerating, and I now take the earth away, now suddenly the box is changing its motion by doing nothing. So therefore we can also say, earth removed, box stops accelerating. So therefore there must be a force from the earth on the box. If you look at all three of these things, right here we've got the box does nothing, but we've just deduced that although it's doing nothing, it's not like there's no forces acting on it. By just our very broad definition of a force, we've deduced there must be two forces acting on it, one from the table and one from the earth, but the box is doing nothing. So there are individual forces, but somehow these forces cancel to not change the motion of the box. So this leads us to Newton's first law, which just says if the net force on an object is equals to 0, then it won't accelerate. So it doesn't say there's no forces acting on the object, it just says somehow these forces add up to be zero, or have the zero effect. We can figure out that effect by just seeing the object is not accelerating at all. Here we've got exactly the opposite. Now we said, well, once I remove the table, there must be a force from the earth on the box. And this just gives us Newton's second law, which says that if the net forces on an object are non-zero, we get acceleration. And we can formalize this by just saying, well, the sum of forces on an object, which we will denote by this sigma, that just means sum of all the forces. Now, forces must be directional, because acceleration, if a force produces acceleration is a vector, so a force must be a vector. So the sum of forces is some sort of sum of vectors, but that is equals to the mass of an object times its acceleration. And that little equation tells me, if you think about the electron we just had, so I've got two completely different phenomena, gravity and electrostatic forces, but in both cases, if I just look at the acceleration that is produced, I can figure out what the magnitude of the forces associated with those phenomena are, without having to really go into the detail of what an electrostatic force really is, or what a gravitational force really is. So this idea of forces is really a great unifying object in physics, so that we can relate various different phenomena to one another.